This is Julianne Schneider, and this is my third lab, the magnetic field of a bar magnet. The purpose of this lab is to find the distance at which different magnetic fields are created from a bar magnet. We use these experimental values to determine the distance dependence of the magnet and the magnetic dipole moment. I found the value of n to be negative 2.93 and the dipole to be 2.3915 amp-meters squared. This lab also includes a coding portion in which we compare the experimental values found with the theoretical values predicted using the Biot-Savart law. The physical principles involved include the Biot-Savart law and the known distance dependence of the magnetic field of a bar magnet. These are both shown below, and we use them as we are doing our calculations and our coding section of this lab. For the procedure, I first downloaded the Teslameter magnetometer app. Then I aligned my phone along the true magnetic north and found where the magnetometer chip was located by finding where Bx was at a maximum and By was at a minimum. I repeated this process and marked the spot as shown in the picture to the left. Then I measured different distances from this location at which the magnitude of the magnetic field was 20, 70, 120, 170, and 220 microtesla. And then, as shown to the bottom left, I measured the off-axis magnetic field. I then used these measurements to find the distance dependence and magnetic dipole moment. When I was doing this lab, I observed that when the magnetometer is far away from the magnet, it measures a near zero magnetic field in the x direction. And as the magnetometer moves closer to the magnet, the measured x component of the magnetic field increases. The measurements I took while doing this lab are shown below. The top picture shows the different measurements at various distances to create the requested magnetic fields in the lab. The graph to the right graphs these values, and the formula shown, y equals negative 2.9284x minus 14.553, becomes very useful in our calculations. The picture in the bottom shows my calculations for the off-axis field, my measurements for the off-axis field, which are very important in the coding section of this lab. To find the distance dependence n, I used the slope of the equation on the previous slide. I could have also used the distance dependence formula shown to the right. I found n to be negative 2.9284, which is good because it was expected to be negative 3 due to the known distance dependence of a bar magnet. To find the dipole moment, I used the formula below and set my intercept negative 14.553 equal to ln of k. Then I rearranged the equation to find that the dipole moment is 2.3915 amp-meters squared. I then used this in my code. After plugging that value in, I created a function for the dipole moment as shown in lines 22 to 26. Then in lines 43 to 48, I created the different observation locations that I was going to use to show the different values of the magnetic field. In lines 53 through 61, I created two arrows for the magnetic field on axis, and in order to find the axis for these arrows, I used the dipole moment function that I created in lines 22 to 26. In lines 66 to 84, I again did the same steps, except this time I did it for the perpendicular locations instead of the ones on axis. In lines 103 to 106, I found the magnetic field for the magnet at the off-axis location, and this is what I use to compare with my value found in the second part of the lab. This is the final result that I saw, and you can see to the left the different arrows for the magnetic fields and to the right the different values found. The value that I found for the magnetic field off-axis using my measurements was very similar to the magnetic field found using my code. This is good because it shows that my measurements were accurate, although the distance that I found was not entirely the same because it was 0.1467 meters with the calculation and 0.2074 with the code. What would have happened if I hadn't oriented my experiment to compensate for the magnetic north and then had instead laid out my meter stick at some intermediate angle with respect to the Earth's magnetic field? If I had done this, my magnetic field results would be skewed due to the magnetic field of the Earth, and I would get different incorrect results for my fields. If I had stuck two identical magnets together to run the experiment again, I would expect the magnetic field to almost double in value due to a difference in distance from the magnets. Thank you. I hope you enjoyed.